Hi, my name is James Walker, and I'm going to talk to you about my work with the development of experimental methods for active charge control using remote sensing methods. Interactions with the plasma environment and spacecraft cause spacecraft to charge. When you have two charged spacecraft in close proximity to each other, they're going to generate electrostatic forces and torques between them. Now, these electrostatic forces and torques can be used in the electrostatic tractor, which is a proposed concept for geostationary debris removal. This technique utilizes the electrostatic forces between the objects to tug a debris object to a disposal orbit. The idea is you have a controlled surfacer equipped with an electron gun, which approaches the target object and applies this electron gun to the target. With the influx of negative particles, the geo debris will charge negative, while the emittance of these negative particles will cause the surfacer to charge positive. With these opposing charges, an attractive Coulomb force is going to be generated between the target and the surfacer. And then using low impulse thrusters, the surfacer will be able to tug the geo debris to a new graveyard orbit where it would no longer be a threat to geo spacecraft. In order to fully implement this technique, we have to be able to control the Coulomb force between the two targets. In order to do this, we must be able to control the potential on each of the two targets, and we will do this using active charge control. Active charge control refers to the use of one or more currents to actively maintain a desired potential on a target. Most work that has gone into active charge control refers to self-active charge control, where we maintain a desired potential on a controlled object. Specifically, this has been used to maintain a neutral charge using ion emitters to maintain neutral charge, which allows for the measurement of low energy electrons and protons. It has also been discussed in terms of Coulomb formations. We're using ion and electron emitters. We can fully control the potential of a surfacer and then perform electrostatic maneuvers. Now, this project deals with target active charge control, where we apply currents to maintain the potential of an uncontrolled target. Now, this has mainly just been discussed specifically in terms of the electrostatic tractor. However, preliminary experiments have been conducted. They used an electron gun and a UV beam to actively control the potential of a target object within a resolution of 20 volts. However, these experiments were a very idealized environment with an electrostatic voltmeter used to measure the target's potential. An electrostatic voltmeter has to be placed really close to the target potential, in this case 3 millimeters, which is not realistic to in situ measurements. And therefore, we want to incorporate remote sensing techniques into our active charge control to have a more realistic charging scenario. The remote science techniques that have been developed in our lab are the electron method and the X-ray method. This project deals with the electron method, so it's the explanation I will give here. A surfacer equipped with a higher energy electron gun aimed at a target will excite secondary electrons from the surface of the target. These secondary electrons will be emitted with a very low energy and repelled away from the negatively charged target towards the positively charged surfacer, where they will impact with an energy equal to the difference between the target and the surfacer. And a retarding potential analyzer is used to measure the kinetic energy of the electrons, and with a measurement of the energy of the electrons and a measurement of the surfacer potential, we can determine the potential on the target. Now, by using a retarding potential analyzer, a voltage sweep must be conducted on the internal grid. Now, this voltage sweep is going to determine the resolution of which the target's potential can be measured at. And to deal with this, we implement two methods for conducting this voltage sweep. The first is an adjusting sweep, where the resolution of the RPA voltage sweep is continually adjusted throughout the experiment. So, for instance, if we are measuring a target voltage range between 0 and 1000 volts, the initial resolution will be 200 volts. So we will measure 0, 200, 400, 600, 800, 1000. And once the target converges to our desired potential, we will adjust the resolution to be 50 volts and conduct the same sweep. And this will continue until you achieve the desired resolution. The constant voltage sweep does not adjust the voltage step throughout the entire experiment. Rather, it is just held at whatever constant value we are measuring. So in the same scenario, for a voltage sweep between 0 and 1000 volts, the voltage step would just be set at 20 and the control would just run as is. Both of these voltage sweep methods are explored in this project, and the results are presented with the rest of the results. One important thing to know throughout this presentation is that the second crossover energy of the second electron yield will define the behavior of the experience. So the only important thing you need to know is that E2, the second crossover energy of the second electron yield, is a stable equilibrium such that the electron impact energy will always tend towards E2. So when we are irradiating a target with an electron beam, the impact energy will be driven to E2, and the impact energy of the electrons is going to be equal to the difference between the electron beam energy and the target potential. So in this way, the electron beam energy and the target potential should have a one-to-one linear relationship, which will be discussed later. Experiments are conducted in the Eclipse vacuum chamber, where control is implemented in LabVIEW. However, the electron gun energy control is manually implemented, and this was to ensure that if any abnormal or significantly large values were achieved with the control, they would not actually be applied to the electron gun and damage it. So we apply a proportional control throughout these experiments. This control is the difference between the measured potential and the goal potential of the target multiplied by some gain. For multiple charging scenarios with different initial potentials, proportional gains, and goal potentials, the control was able to converge to a resolution of at least 50 volts, and in some scenarios, specifically adjusted control with gain less than 1, a resolution of 20 volts was achieved. On the plot on the top right, you will see a dashed line. This dashed line indicates where the voltage sweep was adjusted. And you can see that the potential jumps from 1500 volts up to 1580 volts. The target potential did not actually change. That was just a higher resolution voltage sweep, giving you more accurate measurements. And a similar thing can be seen on the plot on the left, where the potential will be converged to the desired potential and then suddenly jump up. This occurs throughout the results, and this just indicates where the sweep of these RPA potential was adjusted. The figure on the bottom right shows constant potentials, constant voltage sweeps, and you can see that for each of them, the target potential converges with a resolution of 50 volts, and in each scenario with the increasing max voltage, the increasing target potential, the maximum of the voltage sweep also had to be increased, which then increases the time it takes to converge to a desired solution. One thing that we found about these results is that they're robust to pointing errors. So as described earlier, the beam energy and target potential should have this one-to-one linear relationship. The system will always converge to that second crossover energy, so increasing the beam energy by 100 volts should increase the target potential by 100 volts. And this would result in a gain of 1 should have perfect control. But we can see that that is not the case with the floating potentials and the target potential versus time plot with a gain of 1. So with the floating potential, you can see that there is a linear relationship, but the slope is not 1. And then with the control that we applied right, with a gain of 1, you can see that we initially start out at 2300 volts. And in the first step, we achieved that 100 volt goal potential. So in this case, the beam energy was decreased 1300 volts, and we converged the desired solution. But then with the more refined sweep, we find that we're actually at about 1180 volts. So the control decreases the electron beam energy by 180 volts, but the target potential decreases to about 900 volts. So decreasing the energy of the electron gun by 180 volts decreased the potential of the target by more than 200 volts. And we do see that later on we're able to converge to the desired solution. And then when the sweep is refined again, we end up with control that doesn't converge with that 20 volt resolution. Now, this is unexpected because we would expect the control to just converge every single time we adjust the beam energy. And this is likely not the case due to inconsistencies in the impact location of the beam. So when the electron energy of the beam is adjusted, the shape of the electron beam actually changes. So at low energies, the shape of the electron beam is round and large. But as the energy increases, the beam compresses and also adopts an irregular shape. It kind of looks like a cartoon speech bubble. With the change of the electron beam impact shape, the impact location of the beam will also change, which will result in slightly different E2s for each energy of the electron gun. And this is likely what is causing these discrepancies. However, you can see that with a gain of 0.5, we are able to achieve a desired potential on the target of 1,000 volts with a resolution of 20 volts. So even with these inconsistencies in the impact location of the beam, we still are able to pick gains such that the control converges. And this suggests that the control is actually robust to pointing errors within reason. The electron gun has to actually be impacting the target for this control to work. And then next, if we compare the behavior of the adjusting versus the constant sweeps with the adjusting secondary electron method, you can see that the number of steps for each measurement is kept around 10. This ensures that the time for each measurement is relatively consistent and relatively fast. This also means that the control will converge in a similar amount of time for each scenario. So if we go back to the proportional control, you can see that with a gain of 0.5, the time to steady state for the adjusted secondary electron method ranges from about 700 to 1,000 volts. So while this seems like a large difference, this actually only corresponds to like 1 or 2 extra measurements, so a relatively constant convergence time. While with the constant secondary electron method, the time it's going to take to converge is heavily dependent on the voltage range, with larger voltage ranges resulting in larger times to steady state because it just takes longer to achieve a measurement. However, because the voltage sweep does not change and the resolution does not change, this means that we can accurately measure any potential between 0 and that Vmax. So with a voltage range of 0 to 2,500 volts, if the target jumps from 800 to 1,500 volts, the constant secondary electron method will be able to measure that. While with the adjusting secondary electron method, once the control converges, the voltage range is only about plus or minus 100 volts, so we can't accurately measure any potential outside that range. Even with these trade-offs, we can find that using both the constant and the adjusted secondary electron method, the control converges with selected gains. Therefore, active charge control can be achieved using either of these techniques. The specific techniques that will be implemented will depend on the mission requirements. So the conclusions that we can draw from this work is that we can implement remote sensing techniques, specifically the secondary electron method, to perform touchless active charge control of a target and achieve at least 50 volt resolution. However, we can achieve 20 volt resolution given specific circumstances. We also found that we can achieve active charge control of a target using only an electron gun, and this is opposed to previous research where we found we would need an electron gun and an UV laser. We also found that the control is robust to pointing errors with the discrepancies found by the varying E2s, but the control is still able to converge. And then finally, using an adjusting or a constant voltage sweep for the secondary electron method, the control is able to converge. So the specific technique that would be needed to be implemented will depend on the needs of the mission. This work was funded by the DoD through the NDSEG Fellowship Program, and a thank you to the AFOSR for general support enabling electrosag tractor research. These are just the references for this presentation. If you have any questions, please feel free to reach out. Thank you for your time.